Hi, this is the video for section 2.5 of A Student's Guide to the Schrödinger Equation. This section is all about expectation values. It starts out with a little anecdote about Niels Bohr talking about predicting the future. And as it says here, sometimes students are a little surprised to find that you can make predictions in quantum mechanics, which we're all taught from childhood that this is a probabilistic kind of science. It is. But in this section, you're going to learn about making very specific predictions about the average outcome of measurements, as long as you know two things: the operator corresponding to the measurement and the state of the system, which we're going to represent by a ket called psi. The predictions that you're able to make in quantum mechanics are not precise predictions of individual outcomes. They are an expectation value of the observable, which is going to be described in a little more detail later in this section. But for now, just note that the notation for it is to put the observable, in this case just lowercase o, inside angled brackets. That's the expectation value notation. And you can find that expectation value through this expression, in which the operator corresponding to observable o is sandwiched in between the ket representing the state of the system psi and its corresponding bra. So as it says here, this expectation value is the average value of the outcome of a number of measurements. And here it describes what that means, number of measurements. It's not making a measurement and then making the same measurement on the same system a second and third and fourth time. It means making the measurement on a group or ensemble of systems that have all been prepared to initially, that is prior to the measurement, be in the same state. The expectation value is then the average value of those measurements. So it's not an average over time, and it is definitely not the value you expect to get from a single measurement. A practical example of this is to think about the score of all of the soccer matches played on a single day. Let's say the winning sides have an average of 2.4 goals and the average for the losing sides is 1.7 goals. You would never expect to see a score of 2.4 to 1.7. In athletic contests, we score integer numbers of goals. But when you average over multiple matches, then you can see non-integer values for the number of goals scored. So that's helpful in thinking about why the expectation values are not integers, but it doesn't do much for the feature of probability. So in most quantum texts, you're going to find expectation value explained in terms of dice. There's actually a problem like that in the problem section of this chapter if you want to see how that works. But you can also introduce probability to our football match analogy here by saying, okay, let's say that you knew the probabilities of the number of goals on the winning side from 0, which has 0 probability, to greater than 6, which we've also assumed has 0 probability. Remember, this is not meant to represent reality. This is just an example. And 1 goal has a probability of 22% for the winning side, 2 goals, 43%, and so on up to 6 goals. Given that, you can determine the expected number of goals, which we're calling bracket G, for the winning team simply by taking each possible score, which we've called lambda sub n, and multiplying it by the corresponding probability, which we've called p sub n, and then summing those products. So in this case, here you see those sums. 0 goals times 0% probability, 1 goal times 22%, 2 goals times 43%, converted to decimals, of course, all the way up to 6 goals at 3%. If you do those multiplies and add them all together, you get 2.4. That is the expectation value for the number of goals of the winning side. And what did we need to know to calculate that? We needed to know all the possible outcomes and the probability of each. Okay, we can do the same thing in quantum mechanics if we have a Hermitian operator, real eigenvalues because we need real results from our measurements, and a normalized wave function, system in state represented by ket psi. And as we said back in chapter 1, you can write that ket as the summation of a series of amounts, c sub 1, c sub 2, up to c sub n, of these eigenkets that form the ket psi. Here it is in summation notation. We're simply multiplying each eigenket by the amount of that eigenket in ket psi. So what is this expression? Well, let's let this operator operate to the right on the ket. So here's the ket written in terms of the amounts and the basis kets. Here's the operator. We're going to move that inside. Remember, this is a linear operator, so we get to move it right past the constant, and there it is operating on the eigenkets. But we know what an operator does when it operates on an eigenket. It pulls out an eigenvalue. So now we have operating on psi this result. Now compare this to this. What has been the action of the operator? It has pulled out the eigenvalue for each eigenket. Okay, but what we said was we're going to form an inner product with this O psi, and here's the bra that is the dual of ket psi. We've written it in terms of these eigenbras, and these are the complex conjugates of the amounts of each one. So here's how that looks in summation. In order to keep these two summations straight, we've let this index be m as compared to n for the index when we're summing over the ket size. Okay, we can take this, multiply it up here, and this is what we get. Here's our summation over m, here's our summation over n, and we know that we can grab these constants, move those out. That's done here, and since this depends only on m, we can move that in, make an inner product. This is what we now have. But we said these eigenfunctions are orthonormal. That means that this expression, this inner product, equals 0 if n, that's an n, does not equal m. But it equals 1 if n equals m. So that means we can replace this by 1, and these two summations just become this summation over n. Here are these terms. The lambda sub n comes down. The c sub n star times c sub n is the square magnitude of c sub n. So now we see the expectation value of this observable, which we found by doing this expression, is equal to this. And that should look familiar. Let's clean it up a bit. Go back a few pages. And we said the expectation value was just the possible outcomes times the probability of each. So when we look at the expression we just got, this must be the probability of each outcome. Then this expression for expectation value makes sense. It summarizes that right here. If we replace the square magnitude of the c sub n's with p sub n, then this expression produces the expectation value. That is exactly what c sub n squared does represent, as we'll see in chapter 4. Okay, but what if I have a continuous variable, x, so that instead of a set of discrete outcomes, I may have continuous values of outcome? And likewise, instead of discrete probabilities p sub n, I've got a continuous function, p of x. Well, in that case, the expectation value looks like this. The observable is now called x. We've replaced the c sub n's with the continuous variable x. The probabilities p sub n are now the probability density p sub x, and the summation is an integral. This is the continuous equivalent to our previous expression, so we write it like this expression with the x hat operator sandwiched in between the ket psi and the bra psi. And when we take that inner product, here's the complex conjugate of the first member, there's the operator, there's the second member of the inner product. This is how we find the expectation value of a continuous variable. Plenty of examples of that to come. Before we get to those, since this is the last section of the second chapter of Mathematical Foundation, I wanted to introduce a couple more concepts that use the expectation value. This is an extremely important one called uncertainty. In this case, we call that uncertainty delta x, and delta x squared is given by this: the expectation value of x squared minus the square of the expectation value of x. If we take the square root of both sides, that expression looks like this. And where does that come from? Well, if you look on the book's website, you can see that delta x squared is no more than the variance of x. And if you take the square root of that variance, you get the standard deviation of x. So delta x squared is the variance, delta x is the standard deviation. That applies not only to position, but to momentum and to energy. So these expectation values of the observable, or the square of the observable, are extremely important. All right, the main idea of this section is that this expression gives the expectation value of the observable if it's associated with quantum operator O hat and it's in quantum state ket psi. Probably already clear how that's relevant to quantum mechanics, but this little historical note says that Schrödinger didn't know what psi represented when he derived his equation, but later in that same year, Max Born published a paper in which he said, these wave functions psi are related to the probability, and in a footnote, he was even more explicit. He said, the probability is proportional to the square of the quantity that we've called C sub n. This is all contained in the Born rule, which you can read about in Chapter 4. All right, the last section of this chapter, like all chapters, is a set of problems, and I strongly encourage you to work through these. It's one thing to watch someone else and listen to someone else working through this material. You learn at a much deeper level if you do it yourself. And remember, every solution is available on the app and on the book's website. So once again, please take the time to work through these problems. Once you've done that, you're ready to get into the part of the book that really deals with quantum mechanics, starting with Chapter 3 about the Schrödinger equation. Good luck.